Hi, in this video, we want to take a look at creating synthetic data in rows. All right, so we're in the situation where I have a binary target variable, and with this variable, I've got an imbalanced data set, or the data that I have, the proportions do not reflect the known probability of the actual population. So in this example that we're going to go over, what we'll have in our data set is that we know that we should have about 2% of loans should be bad. Well, in the data set, it's about 30%. All right, well, if I build a model off of that, then what will end up happening is that the model will be tailored around 30% for bad observations. Well, that's not really going to be a good model overall, because it's going to predict too large of probabilities of failure on the loan. All right, well, there's a couple things that we could do. We could change the weights in our modeling if that's available for the type of modeling that we're doing. That is what I feel like we should do. We could downsample the bad observations in this situation. So here we would remove the bad until we get about the right proportion. That would be about 14 to 15 observations. That means that we're putting a lot of weight on the 14 to 15 that we choose. Maybe not the best choice, but I feel like this is actually my second favorite. The other option that we could do, we could resample the good versions until we have the right proportions. Now, advantage of this is that it kind of evens things out. We're not putting a lot of faith into a few observations. The disadvantage of this is this throws off the model metrics, because I'm like reusing the data. Any data point that's reused, let's say in training and validation, is going to be optimistic on the metrics form. So there's some disadvantages there. Another option is to create synthetic data. Okay, so when would we do this? So when we have very few observations in one of our levels of our binary data, or we know that a class is underrepresented compared to known proportions. And in general, we should be using weights if we have that option, but sometimes we don't. That's not feasible when we have like very, very few observations, or the desired model does not accept weights. All right, so something I want to say about this, in this example, what we're going to end up doing, we're going to end up generating 20 times as many good observations, so that we have good and bad as our two levels. So good loans, we're going to have 20 times as many good as, 20 times as many synthetic goods as original goods, like the true data. All right, if you think about that, that's too much. That is just too much. I recommend keeping the ratio of synthetic to original about 1-to-1. Any more than that, and you're really putting a lot of faith on your synthetic observations, it would be better to go and explore other options if you have it. But so for this example, I'm going to kind of break this disclaimer, but hopefully this method shines through, because that's what I'm truly going for. Okay, so the first thing I'm going to do is I'm going to load my data. So we're going to use the German credit data from the Caret package. And so here we want to classify a loan as, or predict if a loan will go good or bad. And that way, if it's predicted as bad, or the probability of bad is larger than we would like for a tolerance, then we will not give the person a loan. Now here I'm doing some data prep. I'm just converting the dummy variables to categorical. And here I am creating a new column, doing some data engineering or feature engineering of gender. Okay. So now let's go ahead and let's create a first go around logistic regression model on our data. So on this model, what I'm going to do, I'm going to say that class depends on gender, only on gender, because I want this to kind of shine through what's going on. All right. And then I'm going to go ahead and predict on my model for male and female. All right. So I know that overall loans go bad about 2% of the time. Okay, if loans go bad about 2% of the time, I look down here, this is saying females, a female loan will, so this should be about 0.98. For females, we'll have a good loan about 65% of the time, and for males, about 72% of the time. Well, it's supposed to be about 98. That's pretty far off from that. So what this would lead us to is that we would end up having like very pessimistic numbers. The probability should be around 0.98, but they're closer to 0.7, which is what that's what the proportion is in the actual data set. Well, I mean, that's, if you're going to make a mistake, not giving someone a loan is probably the better mistake to make. But if I want the most accurate model possible, then I want to go ahead and, get the right proportions overall. Now, something about this, what I could do is, if the probability of good is small enough, then I can use the probability as the cutoff instead of using like an imbalanced model. So I really see no advantage to proceeding with the data as is. All right, and let's go ahead and look at a bar plot just so we can see this. So we can see that it's about 0.7 overall, within the data set. We know that it should be about 0.98. Okay, so what we're going to do, I'm going to go through, I'm going to generate synthetic good data, and I misspelled synthetic, but that's okay because we're talking about math and statistics. We're not talking about spelling. All right, and so what I'm going to do, I'm going to use the rows function in the rows package. I'm going to say that class depends on everything. All right, so what happens is this is the target variable, and the right-hand side of the tilde of the formula says these are the variables that need to be included in the generation. If I had only gender there, I would have two columns in the synthetic observations. I would have class and I would have gender, and that's it. So whatever's missing in the formula on the right-hand side will not be included in my synthetic data. That could be good, that could be bad. I want as few columns in there as possible if I'm worried about computation speed. All right, now here I worked out the math beforehand, and we need to add 14,000 more observations. There's only 1,000 in the total data set to even this out the way that we want to be 0.98 overall for good. Okay. Now, something to point out is that when we get output from the rows function, it doesn't directly give me data. It's actually gives us a rows object. I have to go ahead and take the data slot to grab the actual data that I want. And then here, what I'm doing is I'm limiting it only to the good observations. And then I'm only grabbing enough to get the data to the proportions overall that I actually want. Now, something that is a disadvantage about the rows package, the rows function, is that if I look through, it gives me wonky values. So here, age, it's interpreting age as a continuous variable, and it's not putting a bound on it. And we have negative age, we have negative amount, we have negative duration, and this one is a binary variable. All right, well, that doesn't really make sense. And I believe the rest of these should be integers also. That really doesn't make sense. So what I'm going to do, I'm going to go through and I'm going to, and here's what the ranges should be. So I should be from 19 to 75. I should be 250 to about 18,000, 4 to 72, and so on, 0 to 1, and so on down the list. So this shows what is actually in the data. So what I'm doing here to kind of help make sure that my observations are at least within the correct range, I'm rounding off the values because all of these columns had integer values. And then anything that's less than the minimum, if it's less than the minimum, I'm replacing with the minimum in the original data set. So if it's less than the original minimum, it gets replaced by the minimum. If it's less than, or if it's greater than the maximum in the original data set, it gets replaced by the maximum value. Now, if I wanted to be a little bit better about this, I would limit this to data that has only good in there, but I felt like that might be pulling in too much. So remember, if I'm working on a model, extreme observations can basically go and pull the rest of the model away from the other observations. This is what leverage is all about. So if I'm doing logistic regression, I have to, or regular regression, I have to worry about it being pulled disproportionately by large extreme outliers. All right, so now let's take a look. It goes through and it cleans it up. Now, something I could have done, I could have limited this to the values that are inside the inside the good case, but I didn't do that. Maybe I should have. All right, so now let's go ahead and build a new model for logistic regression. I'm going to use my original data and my synthetic good data. And then let's see what the overall predictions are for male and female. Well, when I look at it now, I get pretty close to 0.98. Okay. And so here we can see that it's pretty close to 0.98. Now, something I want to point out to you, you notice that it evened out, right? So we know that's about an 8% difference for the original data set. But now it's virtually zero. That's because of the synthetic data. The synthetic data, which is kind of generating male and female. So this is really not the best way to proceed. This is too much synthetic data to use. But the process works out so that we can see how we would do this. Personally, I would say keep your ratio of synthetic to original data no more than 1-to-1. After that, you're starting to dilute out your values. Well, that's all I've got for you. Take care and goodbye.